So today we're going to be taking a look at a couple of the pre-response questions from the 2000s. And we have here 2003. Where's our question? Hey now. There it is. Okay. So some students physics students build a catapult as shown above. Notice that they very frequently will pull the lab questions from potential labs or projects that a teacher might assign. So some physics teachers are in the habit of assigning a physics project. Sometimes they say your project will be, you will build a trebuchet. You will see how far you can launch a pumpkin or something like that. And sometimes this get pretty exciting. The college level trebuchets can often chunk a pumpkin, good 100, 150. Sporting platform is fixed firmly to the ground. The projectile of mass 10 kilograms is placed in cup A at one end of the rotating arm. A counterweight bucket B that is to be loaded with various masses greater than 10 kilograms is located at the other end of the arm. The arm is released from the horizontal position shown in figure 1 and begins to rotate. There is a mechanism not shown that stops the arm in the vertical position, allowing the projectile to be launched with the horizontal velocity as shown. A. Students load 5 different masses in the counterweight bucket, release the catapult, measure the resulting distance x traveled by the 10 kilogram projectile according to the following data. Mass, blah, 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 x, blah, blah, blah. Now, what we have here is a question. You guys have seen us do this before. We have the stem of the question. And the purpose of the stem is to set up the question and to give you basic information that applies to all parts of the question, unless otherwise specified. And also, it serves to eliminate any sources of misunderstanding or to provide simplifying assumptions. Where do we see, first of all, some statements that help us to make simplifying assumptions?
Not quite sure what you're asking.
Well, for example, okay, some students build a catapult as shown above. What that's doing is simply identifying the nature of the problem, right? Then we have the supporting platform is fixed firmly to the ground.
So you don't have to break out if moving at all.
Yes, that's exactly right. You may assume, therefore, that there is not going to be any recoil in this. Okay. And so that immediately allows us to sort of scratch like conservation of momentum type approaches off our list of potential ways to do this. So the purpose of this sentence right here is to help focus our attention on some stuff. All right. The projectile of mass 10 kilograms is placed in cup A at the end of the rotating arm. What is that word rotating doing for you?
What kind of direction are we going in?
Yes. So we knew that it was rotating right here, but by drawing our attention to it, it now kind of sparks all those thoughts about rotation. So these words are very often little breadcrumbs that they give that will kind of help us to figure out what approach we're going to take. A counterweight bucket B that is loaded is located at the other end of the arm. Okay, the arm is released from the horizontal position and begins rotating. There's the mechanism that stops the arm in the vertical position, etc. Then we have a bunch of data, and our first direction is found right here. Sketch a best fit curve for these data points. Okay. Now we consider, what do I need to know in order to sketch the best fit curve? Not much. Curve. Right. I just need to know the data. And I see the data right there, and so I'm ready to sketch the curve. And at this point, I'm not going to trouble myself with any of the information up in the stem, because I've got one job, sketch that best fit curve. What are the characteristics of a best fit curve? Smooth?
This one looks,
Like, square root of x, kind of like that.
What
What's
kind of
up?
look like a square root or possibly an exponential upside down?
yeah.
Turns out it's probably a square root, but it's in that neighborhood, right? Okay. What other characteristics do best fit curves have to have? Well, no.
If the, if the,
Good. No, actually, a best fit line does not have to go through any points
so a
whatsoever.
best fit line and a best fit curve, do you approach them differently? Because I know the best fit line is like you have data points that are like a little bit off, you just kind of like have a couple over top and a couple below.
Yes, exactly. And that's what we want to do. We want to make sure that there are going to be, to the best of our ability, either that our curve goes through data points or that it has points above and points below. So I can draw myself a smooth curve. Notice that, well, I can draw pretty well a smooth curve like so, and that's pretty good. As long as you've got, notice I've got a point that's peeking out above right there, point that's peeking out below right there, and here it is. The key is that you do not want to have all points below, nor do you want to have all points above. You want to, I call it threading the needle. Right. So there's my curve with the following characteristics. Smooth. So we are not connecting the dots. Sometimes I'll get curves that are like, you got some points here, and somebody will go, this is not an acceptable best fit curve. And we have points above and below. And in this case, it's possible to draw it so it kind of goes through all of them. So we'll put 4 through. Using your best fit curve, determine the distance x traveled by the projectile of 250 kilograms is placed in the counterweight bucket. This phrase, using, is one of my favorite phrases because it is focusing my attention on how I am supposed to do this. I am not supposed to, again, use any of the information in the STEM. I'm supposed to only use the best fit curve. And so I consider how might I do that. Determine the distance x. Oh, look, x is on this axis. The travel by the projectile if 250 kilograms is placed in the counterweight bucket. 250 kilograms placed in the counterweight bucket. This is the mass placed in the counterweight bucket. 250 is going to be found. Oh, gotta be careful. Is it found here? Let me check. That number is 300. So 250 there. So on my best fit curve, I get this point, and reading this point, making sure that I'm reading the axes correctly, that's 35. And so I'm going to be somewhere between 30 and 35, a little bit less than halfway. I call that 31. And there it is. Okay. Questions on that? Everything's a-okay, so. The students assume that the mass of the rotating arm, the cup, and the counterweight bucket can be neglected. With this assumption, they developed a theoretical model for x as a function of the counterweight mass using the relationship x equals vxt, where v is the horizontal velocity of the projectile as it leaves the cup, and t is the time after launch. It's not always profitable, but sometimes my mind can't help itself. When I look at this relationship right here, I think to myself, what?
Projectile motion.
Standard projectile motion. That's exactly right. We've got a relationship like this because gravity pulls straight down and not in the horizontal direction. Okay. How many seconds after leaving the cup will the projectile strike the ground? Okay. Now, here's an interesting question. Are they referring to the situation in part A, or are they referring to the general situation? In other words, do I want my answer to be numeric, or do I want my answer to be T in terms of all these other things here? And so, since that is ambiguous, I also ask the question, does it matter? Ooh, right? So when I hit a question that is ambiguous, maybe it's this and maybe it's that, sometimes the answer is maybe it doesn't matter. So let me go back and see, maybe this doesn't matter. I wonder why not. So I consider, all right, given that I'm thinking projectile motion, how would I determine how long it takes for the particle to hit the ground?
I split it in X and Y.
There we go. That's right. Let me bust out my projectile motion. X and Y. And what do we have in the X in the Y direction here?
You can use the kinematics equation, which is y equals v0t plus 1/2 gt squared.
Does gravity go up on your planet?
I mean minus 1/2 gt. That would be
That'd be a very dangerous planet.
Okay. And it could just be that you had a direction in mind, the down is plus, and then maybe you were going to give me something else. Okay, well, let's see if we can fill these things in. Do we have, and also, shouldn't this be delta y?
Yeah.
Okay. Or you could say y equals y0.
Right.
So now let's see if we can fill in the details. What do you have?
Delta y equals 15, because it's the 3 plus the 12,
Okay.
and v0y is 0,
Aha.
because all of the velocity is all horizontal.
And
And then you have minus 1/2 gt squared.
which is minus number.
Oh, 5, minus 5 t squared.
Now do a little bit of look ahead. Does anything bother you about this equation?
Time is going to be negative.
No, it's not. Time is going to be the square root of a negative, which is
Oh.
imaginary. Wait a second. What happened? Yep.
The displacement should be negative. Because
Yeah.
final is 0 initially.
So we had a very common student error. We had a sign problem or a failure to take direction into account. Which way is positive for the problem? And what's the displacement? Down.
Yeah.
Take a look at your projectile. Which way is it moving?
Oh.
Right.
My bad.
Yep. Sometimes because of that, I find that this is a little bit less error prone.
Okay.
A little bit less because I can now identify positions, and that'll help. So then I can say on the ground equals initial position minus 1/2 gt squared, and my equation is solved. So now what do you notice about the solution to this equation? First of all, what is that solution?
Root 3.
Root 3.
Which was 1.7.
What do we notice about the solution to our problem? It made the ambiguity go away. And then we remember, oh yeah, dropped bullet, launched bullet, they both hit the ground at the same time. The initial speed doesn't matter. And so in all of these circumstances, it still takes the same amount of time for the projectile to hit the ground, which is kind of cool. Write an equation that describes the gravitational potential energy of the system relative to ground when it is in the position shown in figure 1, assuming the mass in the counterweight bucket is m, and then derive the equation for the velocity of the projectile as it leaves the cup as shown in figure 2. Okay. So reading this, I know I'm going to have to go back and do gravitational potential energy, blah, blah, blah. What what does 2 suggest about our approach in 3?
That, what we get into will be used in 3.
And therefore, what approach are we probably going to use?
Energy
Energy specifically
conservation.
because we're dealing with,
Gravity.
and also because we're dealing with a potential energy function here, right? So it strongly suggests that we're going to do conservation energy. All right, well, let's go back and do that. Because we know we can do conservation, or we can do potential energy for gravity all day long. U equals? Absolutely. And now we just need to fill in the details.
Oh, shoot.
Yeah.
Wow.
Notice that everything here has been really simple stuff that you know.
Yeah.
What's the thing that's different?
The way they're asking me, I guess.
Forces you to do what?
Break it down.
Yes, because they're asking you questions that make you do everything all at once.
Yeah.
That is the only thing that is challenging about the AP problems in general. Each individual step you can do,
Mm-hmm.
but now you have to have the presence of mind to recognize to do it.
Mm-hmm.
Okay. Well, go ahead and compute that. Are we supposed to calculate the potential energy in figure 1 or figure 2 according to the problem?
Figure 1.
Figure 1. All right, go.
So we'll start with the projectile.
Mm-hmm.
A mass of 10,
Mm-hmm.
G of 10, and a height of 3.
Mm-hmm.
And plus a mass of capital M times 10 times 3. So let's start again.
Okay. Now, in the next part of this, they asked us to compute, write an expression for the speed, and I believe it's supposed to be in terms of m. Is that correct?
No.
And it didn't say what terms.
Ooh,
Says-
interesting.
So I guess we have to, maybe M's will cancel.
Maybe the m's will cancel. Maybe they won't, because I've got a term without an m here. So,
Yeah.
so I'm not sure. It may very well be that the mass is relevant to our speed, and let's see what the computations do, and then let's come back and think about it in physical terms. All right? How are we going to proceed?
Set up conservation energy,
Go.
which is U final, U initial plus K initial equals U final plus K final. K initial is 0.
Mm-hmm.
We have to U final, so we know U initial, which is 300 plus 30M.
Mm-hmm.
U final is, so the mass is left the cup, or has, well, yeah, the mass is left the cup.
I don't think so.
Q,
I think this is right at the point
right
where,
before,
like right before it stops.
so is there a velocity then?
Interesting. It's ambiguous. So what's the question we ask?
Does it matter?
Does it matter?
Doesn't matter.
If the mass has left the cup,
Mhm.
then isn't the mass that has left the cup still part of my system?
Yes.
Okay then. So right at the moment that it leaves the cup, whether it's, we think it's still in the cup, or just exiting the cup, it's still part of our system, so we still have to account for it. Okay, so we have 10 kilograms, times 15,
Oh, okay.
Because
times 10.
Okay, oh, gotcha. And
And
then
count away.
the height is 1, right? Yeah, 3 minus 2.
Yes, the height is 1, good catch. Right.
I was
Okay, so what is the?
It's 10 m.
Okay. What else?
we still have to do K final.
We still have to do K final.
Could we use 1/2 I omega squared here?
We can. Um, yes, we can.
But is it wise?
Well, let's actually walk down that. First of all, what suggests that we might want to use 1/2 I omega squared?
We're rotating.
We're rotating. So let's consider that. If we do 1/2 I omega squared, I'm going to need to compute I, and I'm going to need to relate omega to what I'm trying to find. What am I trying to find? The speed v. Okay, can I do that? Well, to compute I, is this an easy or a hard computation? Easy, because I have 2 point masses. All right, that's cool. And what about the omega? Can I relate that to the v that I'm looking for? Oh, this goes back to your question you asked me. What's that? V equals r omega, but what radius would I use? I would use the 12 because that's the radius of the point whose velocity I see.
Okay, so we can take this as rolling without slipping, or just kind of rotating.
It's rotating, right? So in general, if you have a point going around an object, V is going around another point, rotating around another point. V is equal to r omega.
I always think of that relation in like something rolling,
Yeah.
and it messes me up.
So that's actually a different circumstance.
Okay.
When an object is rolling, it happens to be the case. So for instance, it happens to be the case that if an object is rolling without slipping, the velocity of its center of mass must exactly equal r
Okay.
omega. Yeah.
All right.
But that's different. That's so that it's not slipping.
Mm-hmm.
Okay. Okay, let's do it. 1/2 I omega squared. First of all, the I. Do some cleanup here.
I equals capital M times 2 squared plus 10 times 12.
40. Okay. What about the omega?
Omega equals V over R squared.
And the R?
The R is 12.
Yep. There you go. Notice along the way that Austin cleared up a misconception about the radius, about rotational motion, right? So he has a distinction now that V equals R omega under 2 different circumstances that didn't know before. All right,
Now, just looking ahead, unless a miracle occurs, it is going to be the case that my velocity is going to be equal, is going to be a function of the mass m. Does everybody see that? If I solve for v, by the way, I've got the wrong label here, because what is that velocity called in the problem? How is it labeled?
Yeah.
Vx. And so I need to be careful to use the same labels that they do.
Wait. Oh, okay, yeah, I see it. Got it. My bad.
I need to be careful to use the same labels that they do and use check. Velocity as well as Vx. All right.
Oh, because we're gonna relate it to the theoretical relationship.
Yeah, that's right.
Got it.
Okay. So, question. Is that an acceptable result physically? Should it be the case, do I have any evidence that the mass actually changes the velocity?
Yes,
Yeah, what is that evidence?
we go further and further in X.
Yes. Okay, so I'm actually happy with this result. I wasn't sure if they wanted mass, and I see they have to want mass here.
Right, because if the time stays the same.
Yes. Exactly, that's exactly right. Okay, so it's a matter of solving this equation, kind of a pain in the neck, but I think I can do it. So we're going to have 1,500 here, and we're going to have another 720 there, so that's 2220 plus 10m plus a half of 4m is 12m. Oh, no, wrong, bad. A little bit of algebra mistake there. That's, yeah, actually, so algebra mistake all the way through. Let's subtract terms so we can clean up our lives. Minus 1200 plus 20m is equal to half of 4m plus 1440 is Vx over 12 squared. Multiply by 2. Divide by 4m plus 1440. Don't worry about the common factors. And that's equal to Vx over 12 squared. And now, let me copy all this over. Take a square root. Make sure I got the right numbers here. 40, got it.
Hey, it was
I can get that right there. Can this be simplified? Yeah, probably. Am I going to? Absolutely not. The philosophy on the exam is once you have something algebraically equivalent to the correct answer, you're done. That's not a 4.0, by the way. It's just a stray mark. How did I get 40? Back over here.
3 times the 3 times the 20 minutes.
That's right. So we're multiplying both sides by 2. Right? Just solving. Just algebra. Hopefully good algebra.
Always
Okay, so notice that this question slowed us down a whole lot, right? So stepping out of the role of answering an AP question and into the role of learning, we recognize that this bottleneck of having to slow down and think about it is a bottleneck we want to eliminate mentally. And so this is a point where I want to go back and talk through this problem the second time at this point so that I can become efficient in my thinking about it. Does that make sense? A lot of the payoff in doing these problems is not going to come from doing them the first time, but from thinking them through the second time so that you can become efficient. Okay. Well, we've done all of that. We're happy and proud of ourselves because it seems like this part was a lot of work, and we hope the rest of the parts go quickly because we spent a lot of time on it. Okay, complete the theoretical model by writing a relationship for x as a function of the counterweight mass using the results from here and here. Well, if I look at the results from there and there, I have a result for Vx, which was sort of complicated. It was 12 root blah, blah, blah. And I also have a time in the other part that was equal to root 3. Well, I am no dummy. The theoretical model they wanted was x equals vxt, and hey, I can do that. On the real paper, I would not put the dot by dots, obviously. Compare the experimental and theoretical values of x for a counterweight bucket of mass 300 kilograms. Where am I going to get the experimental value? From the data, from your best fit curve. Or maybe the data table. Am I lucky enough to have a 300 on there? Yes. Okay. Should I use the 300 experimental data or the 300 best fit curve?
Experimental.
Ooh, interesting. That's a really interesting question. So it turns out that scientists kind of put a premium on the best fit curve because they consider the experimental data might have random errors in it.
Really?
Yeah. Now, in this case, the data are so close to the curve that, in fact, Euler's curve goes through the data point, so it kind of doesn't matter. And I think they would actually accept either one.
So I know this one, yeah, like you said, most of the points are through, but if we have like a best fit line where the points are a little scattered,
Yeah.
we would definitely use the best fit line instead of the point that was exactly at 30.
Yes, and the specific reasoning is this. You have a theoretical model that you've just developed. Notice that it is a sort of square rootish curve. Okay? Then that theoretical model we are trying to compare to the experimental results. The experimental results we are assuming are basically equal to our best fit curve plus some random error. It is the best fit curve that we are trying to compare to our theoretical model.
Cool.
Yep. So speaking of, where am I going to get the theoretical value of x from the curve right here?
So you plug in 300.
So you plug in 300,
Just like the
plug
movie.
in mass, and there it is. There will almost assuredly be a reason for a difference. If the difference is high, what kinds of reasons? Well, let's actually do that. What numbers do you get?
Minus 2400 plus 12,000 in the numerator,
Yeah.
and then 1200.
You can go ahead and do that in the calculator. Meanwhile, what do we have for the experimental result? Yeah, about right. X is 37 meters. Let's keep our units here. And what's our theoretical?
It is 39.6.
You got what? You got 42 from the same theoretical model? That's interesting. Let's see here. Looking at Daniel's calculation. I don't see anything wrong. It's all in one line. Oh, wait, yes, it should be 2400.
I get 39.6.
Yeah, so did she. Well, she fixes that. Did you try to be fancy? Did you try to be fancy and simplify?
Oh, no. When I multiply here, like, I do have, no, I do have the right thing here, but when I'm writing the equation, I do that
When you
right.
typed it in, yeah. By the way, because you did it all in one line, I was able to easily look at it and check, right? Yep. Okay, so what do we observe about the theoretical compared to the experimental? Mhm. Okay, in 2 words, what does this indicate somewhere? Think about how we derived our theoretical model. What approach did we use?
Conservation of energy.
And so if the theoretical model is bigger than the experimental, it indicates in 2 words.
Some good identity as well.
Exactly, energy loss.
Energy
That's
loss.
right. So now we just have to account for energy loss in some way or another. What do you think is the best explanation? What are some potential explanations for energy loss?
Air resistance.
Air resistance is one of those.
Friction in the pivot.
Friction in the pivot is another one. And the third?
Um,
Sound. You actually do use a little bit of energy to sound. Couple joules.
really?
Actually, not much. Ooh, interesting. It might be millijoules. Yeah, I think
They haven't grown up yet.
Alright. There's one more.
Friction in the pivot, air resistance.
Is there any part of the process that we just ignored? Yeah. What's that?
That's been free to be seen.
And how does that releasing happen? Describe that process.
It has this, the arm stops.
How does the arm stop?
There's a mechanism that we don't see.
That we don't
Yeah.
see. What kind of process is that?
It decelerates beyond.
Quickly.
Yeah, we have a name for this process going on.
Oh, it's a collision.
It's a collision. Right. Is it a totally
Yes.
elastic collision?
Probably not.
No.
Because
is not.
they stick. Well,
Right.
essentially they
Yeah, they
stick.
essentially stick. Right. So energy loss candidates are air resistance, sound, friction in the pivot, and the collision with the stopper. Of those, rank them in order in terms of energy loss, from high to low. Those 4. I'll write them down for you.
Ooh. Price is right, actually.
Yeah. Okay. How would you rate them, Danielle?
I said the collision loss is number 1, and then friction to number 2, and air resistance, and then sound.
Good. How come you didn't rate air resistance very high?
I don't know, but I think
Okay, intuitively, how can we tell if air resistance is going to be high or low for a given object
Surface area,
compared to
the mass.
the mass? That's right. If the ratio of mass over area is large, the air resistance is going to be low. You know what? That's an inverse relation. Let's flip it. If
the ratio of area to mass is large, the air resistance will be large. And if the ratio of area to mass is small, the air resistance will be small. So insects have a relatively large surface area to mass. Cannonballs do not. Trucks are interesting. Trucks actually have a fairly low profile compared to their mass, but they're going at such high speeds. Whereas here, we're going at moderate speeds. So we understand, we remember our models for air resistance, right? R equals either negative BV for laminar or negative BV squared for turbulent. Trucks are actually going fast enough that they experience turbulent air resistance. And you may have seen some of those trucks with the spoilers on the back, those 4-panel things kind of open. That's basically reducing the air resistance because it's reducing the sharp corner that you have that causes eddies and turbulence. And the eddies right here basically create a little bit of back pressure that slow that truck down.
So, I was watching some type of car show, and they had a truck and a car like tracking really closely behind it, and they were going like 55, both of them. They were like on the radio, so they wouldn't crash anything. But the miles per gallon that the car was getting was super crazy.
Yeah.
Because like he was so close to the truck.
Yeah, yeah,
He didn't have any air resistance on him.
yep.
I thought that was
Yeah, you got your truck with the laminar airflow. If the truck is properly configured, all of that air is going to flow right over the top of the car.
Yeah.
Which doesn't mean there's no air there.
Right.
You're not worried about suffocation. It just means that there is not a flow. Right. In terms of actual magnitudes, the magnitude of the collision is going to swamp the magnitude of the other 3 factors. If you said air resistance, my guess is they might not have given you credit. If you look at the solution.
If you said just air resistance?
Yeah, I don't think air resistance is meaningful. If you said sound well, you get a lot more.
But if you
I'm not dissing what you said because that is a real energy loss. It's just small in magnitude.
So that's why you want to say more than 1.
No, actually, I would just say 1. But in terms of thinking about them, I want to think of 1 and then rate 5.